Good afternoon. So our next speaker in this keynote hardly needs an introduction. She's very well known for her work on the spanning tree protocol and TRILL, and we're really excited to have you here. And she's been working with Sun for quite a number of years, and lately with Intel. So please welcome Radia Perlman.
Okay, so I have to talk fast because I only have a half hour. So all opinions expressed here are mine, though I hope I share these opinions with lots of other people independently. So network protocols, a lot of what we all know is actually false. The way networking tends to be taught is here, memorize all of these RFCs. This is how networking works, as if, it arrived, TCP IP arrived on tablets from the sky in its awesome perfection. And nothing else ever existed except to make snide comments about. So if you mention ISO, you're supposed to giggle about what morons they are or something, but you're not supposed to know anything about it. Things are very confusing. So one of the things I really like to do is get to the heart of what is the difference between A and B. And it's very, very difficult because nobody knows them both. So if you ask people who know about A, how does it compare with B? They say, well, A is awesome and B sucks. And then you ask B and you get the same answer. And then if you point out to the A people that there's features of B that make it superior, there's no problem. The A people steal the ideas. So you have these two different moving targets, and to try to actually get to what's actually there is extremely difficult. So how I wish we'd compare, isolate the conceptual pieces and ignore which team. A lot of times I tell people, you'd like to think of, standards committees as kind of well-educated technologists discussing, technology, but instead it's more accurate to think of them as drunken sports fans. It's sort of my team versus, whatever. So there's all sorts of orthogonal ways in which networks can differ, and I picked a few that I thought could fit in a half hour. So what information is in a packet? Who computes the forwarding table? Is the forwarding table just there in the switch so it always knows what to do when it sees a packet, or does it have to, when it sees a new kind of packet, go and create a path on demand? Whether the switch can choose among multiple next hops or only has a single way to go, how to translate from a layer 3 address to a layer 2 address, all these kinds of things are ways in which things can differ that I'll talk about in the talk, but there's other things too that I could have talked about. So what does a switch do? It forwards based on information in the packet. And so typically in a packet, there's a destination address, and then if you need to keep things in order, there's other stuff like the TCP ports, or you could have a flow ID field or an entropy field to help you choose among multiple hops. In the forwarding table, you could have a destination address that maps to a single output port and the switch doesn't have to have any other choices. Or it can be a destination address that you look up and it gives you a set of ports, any of which are okay. Or it could be a flow, which is sort of a whole bunch of things in the packet, like not only the destination address, but the source address and the TCP ports, and that would map to a single port. So there's different types of destination lookup. One is a direct lookup, where you take the destination address and immediately index it into your forwarding table. This is simple and fast, but it requires, it can only be done if the address is small enough that a table that's the size of the, 2 to the size of the address can fit. Another possibility is a hash. So if you're trying to look up an Ethernet address, you're going to have to hash it because it's kind of too big. Another thing is IP, which is also too big, but you structure it in a way that you're really looking up a longest prefix. Yeah, now some thoughts. Suppose you want to forward based on a flow versus a destination. Well, it's hard enough to have a forwarding table which is the size of the number of destinations. If you want to have a forwarding table that will be big enough to have all of your flows, not just all the destinations, but all the source destination pairs, and worse than that, all the source destination pair TCP ports kind of thing. The only way this can possibly work is if the forwarding table doesn't know what to do with everything, and when you see a new flow, you incur latency when you try to figure out what am I supposed to do with this new kind of packet. So that incurs a latency when a new flow starts up. Another thing is that, like people say, well, the flow-based is really better because if there's a central fabric manager that has complete knowledge, then it can allocate the flows to distribute the load better. Well, that's, kind of only if flows, and this is kind of an old-fashioned idea that a lot of people believe, that what a flow is that it starts up at a certain bandwidth, and it keeps that bandwidth for days, and you have like all the time in the world to kind of adjust your window. I think traffic is going to be bursting in general. So even if you know where all the flows are, that doesn't give you any sort of momentary knowledge of what the queues are going to be any place. So I think that a switch is in a much better place to be able to see right now which links are getting congested and make a choice. When it has multiple next hops, it can make a choice which way to go rather than right in advance assuming based on flows. And if a switch has to keep packets of a particular flow in order, then it's kind of constrained to do some sort of hash further in the packet in order to hash it to always choose the same next hop. But even then, if the switch is noticing that some link is sort of more congested, it could redo the hashing algorithm to adjust it to make more flows go onto different links. So, exploiting parallel paths, a topology like this, where S can send to any of the next hops, any of the R1s can send to any of the R2s, then the switch can have a forwarding table and exploit this to spread the traffic around. So now a completely orthogonal topic. So I'm going to be talking to you about a bunch of completely orthogonal things. Like people tell me things like Ethernet is fat tree. It's like, no, the topology is completely orthogonal. You can build anything on any tree. So anyway, so the things I'm telling you, try to remember that they're all separate pieces that are orthogonal. So where does the forwarding table come from? It could be a distributed algorithm, or it could be a central fabric manager. Neither concept's new. Many networks have been built both ways. So ATM had a central fabric manager, I believe. InfiniBand assumes a central fabric manager. IP assumes a distributed algorithm, but you could actually have built IP with a central fabric manager or whatever. I think that and the concept of separation of control plane from data plane is also not new. But I think a distributed algorithm is superior, because if a link changes with like a link state routing protocol, which is a typical distributed algorithm, information that link has changed propagates outward as quickly as information can move, and all of the switches, as they receive this information that gets flooded outward from the event, adjust their own tables. With a central fabric manager, a link dies. Somehow you assume that you can still reach the fabric manager, but let's assume that you can. So you have to tell the fabric manager that link changed. The fabric manager has to recalculate all of the forwarding tables and then go and adjust everybody's forwarding tables. So sure, fabric manager, central fabric manager, it works, but I think distributed algorithm is actually a superior way to create the tables. And some people say, well, if we can get rid of the routing algorithm, switches now become incredibly cheap. No, that's not what makes switches expensive. It's not the routing algorithm. It's the, how do you move bits that quickly between the ports? It's not the control plane, it's the data plane that makes it challenging to build a switch. Another thing that's completely orthogonal, people say, oh, Ethernet switches are so complicated. There's all this extra junk in them. What kind of extra junk is there? Well, things like, firewalls or intrusion detection things or SSL session termination or NATs or other things that have to keep state, multipathing, traffic engineering and bandwidth guarantees, ports that can not only do layer 2 but also IPv4 and IPv6, IP multicast. All these sorts of things are, you don't have to do them if you're doing Ethernet. But you can, and if you're doing something other than Ethernet, if people want these things, you still have to put them in. So another orthogonal thing is, when does the forwarding table get filled in? So one is proactively. That means that a switch has all the information it needs to handle any packet it sees, and the forwarding table only changes if the topology changes because a link goes down or whatever. And another way you could do it is when a flow starts. And it sure seems to me that having all the information necessary to do what you need to do is a better thing to do, because proactively means you see a new packet, then you have to go and create a forwarding table entry somehow, and this will be a delay when you first start sending. And is that acceptable? And why would you want to do that? Another orthogonal thing is, how do you manage a network? I don't really manage networks, but the only time I kind of was, visiting some major ISP, and this was many years ago, decades ago, there was this room where they managed the entire network from. And there was a big screen that showed a picture of the network with links that were blinking red if they were, if they were down, and other ones that were congested, and they could manage certain things from the console. And so there were some big commands, the guy was not typing ASN1 SNMP commands. It was, some sort of the kinds of things you would want to do when managing the network, whatever that was. And it would get translated into whatever you needed to do to tell the switches. So it was not that a person went around toggling switches on each, toggling things on each of the switches. It was one place. And that, I believe, is the only way to manage a network, and I believe that's, probably how everybody does it. If anybody else has, an example of how networks are managed, I would love to see it. And every time you define a protocol, you define parameters that are settable, readable, and events that trigger alerts, and these things, communicate to the central management thing. So there's various management commands to the switches, various protocols for doing that. There's SNMP and netconf and Yang and OpenFlow. And this is not something I've paid a lot of attention to. People seem to be very emotional about one versus another. I would hope that the human being doesn't, who's managing the network, doesn't even know which one is happening underneath. Like I asked someone who, oh, there's this netconf and Yang, why are they doing that? And they're saying, oh, because SNMP is horrible. And it's like, what about it is horrible? I don't know. But, so that's something that I would be curious to explore at some point. But it seems to me that it's all the same, that you have big commands that the manager decides what they want to manage, and somehow through some protocol, that management thing tells the switches to, change whatever it needs to change. So now I'm going to sort out a few existing things. So there's IP, there's Ethernet, there's TRILL, and then I'll talk about some other things as well. How do these all fit together? So a bit of layer 3 history that you'll never learn in any networking text except for mine. Is that ISO had a layer 3 protocol known as CLNP, Connectionless Network Layer Protocol. It was very, if you understand IP, you will be very comfortable with it. It's just a destination, a source, a hop count, other things. It had a 20-byte address. But the thing that's very different about it than IP is that the top 14 bytes of the 20-byte address was to an entire cloud, as opposed to an IP where the address specifies, the prefix specifies a particular link. And IP routes to an exact link. Every link has to have its own block of addresses. But with CLNP, you could have this large cloud that inside, it was a flat address space you could move around and you could keep your address. So inside of the cloud, you didn't need to configure the switches at all. Somebody had to know what the 14-byte prefix of that cloud was, and it told everybody else. But other than that, the routers were as zero configuration as the original transparent bridges. So a router would look at the top 14 bytes and say, is that the same as my cloud? Yes, it is. Then I have to look at the bottom 6 bytes and route based on exact match of that. EndNodes helped out by announcing to the routers, I'm here, so that the routers within a cloud could keep track of where the EndNodes were. So so there was this 14-byte thing that says which cloud you're in, and then the bottom 6 bytes was your EndNode address within that cloud. In contrast with IP, every link has its own prefix, routers need to be configured, and if a node moves, its address has to change. So with this hierarchical thing, if you have one prefix for the campus, the routers don't need to be configured, it's a flat address space, the EndNodes can move. Whereas with IP, if you have a block of IP addresses that start with a 2, you have to carve it up, giving a unique block to each link, and the routers have to know which blocks are on which ports, and if an EndNode moves, it has to change its address. So advantages of CLNP over IP is you don't need to configure the routers inside of a cloud. There's a flat address space. I'm just saying the same thing over. So nodes can move within the cloud without changing their address. There was also no need for ARP because the flat address space was part of the 20-byte address. So once you got to the cloud, you knew how to route to the EndNode. You didn't have to do this translation of layer 3 to layer 2 like is done in IP. And there's other things that there isn't enough time to go into. So the worst decision ever in the history of mankind was that in 1992, people said, IP addresses are too small. Why don't we replace IP with CLNP? And a few people just went berserk, saying, oh my gosh, are you suggesting that we rip the heart out of the internet and put in this foreign substance? And they objected to things like ISO's layer 5. It's like, we're not talking about that. We're talking about replacing the layer 3 packet format of IP with the layer 3 packet format of ISO. But, because, now imagine if they hadn't kind of had this amazing not invented here moment and had said, okay, let's just take CLNP, all the vendors have implemented it, it's good enough. We would have been using bigger addresses for the internet years ago. 1992, the internet was nothing, it was this researchy thing. And it would have been very easy. And also IP at that point hadn't invented, these kludges that have allowed us to live with it and continue to live with it, like DHCP and NAT and so forth. And you'd think, well, at least IPv6 is going to save us. Well, if you've worked on something for 20 years, beyond when a perfectly acceptable solution was there, you would hope that it would be technically superior, spectacularly so, because you had 2 decades. But it's actually inferior to CLNP in a lot of important ways. Like, for instance, IPv6 still assumes that you route to a particular link. So that's why we're stuck with both Ethernet and IP. In order to create a cloud with a flat address space for IP, because IP doesn't do that, it just routes to a particular link, that's why we need to build big links, and we build big links out of Ethernet. The original Ethernet was CSMA-CD. That died long ago, so people think Ethernet is a successful technology. The invention of it, the CSMA-CD stuff, doesn't exist anymore. It's all point-to-point links with spanning tree. And that's another really cool story of how it got to be spanning tree, but don't worry about it. The constraint in 1983, when trying to design a way to interconnect these Ethernets, was that we were not allowed to change the Ethernet frame in any way, including we couldn't add to the length, and we couldn't depend on the end node helping out in any way. So, what we basically did was just say, okay, just move the packets around, but it can't have any loops, so you have the bridges calculate a distributed algorithm that comes up with a subset of the topology that doesn't have loops, which is a spanning tree. So spanning tree doesn't give optimal paths. So it shuts off some of the ports so that there's only one way to get from any place to any other place. So if you look at A's path to X, it's this really long path, 11, 7, 6, 2, 14, 4, 3x. And you might think, well, if only we're a smarter spanning tree algorithm. No, it's once you have a single shared tree. If you imagine the topology being a big circle, you have to chop it someplace, and people on either side have to go the long way. Then, for some reason, mysteriously, IEEE decided that there was no longer any length restriction. They'd say, well, you can always sort of assume that you have an extra 50 bytes or whatever for extra headers. So because that's no longer a problem, it was possible to invent TRILL, which stands for Transparent Interconnection of Lots of Links. So it allows clouds with a flat address space. It's just like Ethernet, but it's a better Ethernet. It's one that allows optimal paths, multipathing, anything you could do at layer 3. It's evolutionary in the sense that you can take an existing spanning tree Ethernet, replace any subset of the switches with TRILL switches, and the more you replace, the better bandwidth you get and the more stable it gets. But anyone that doesn't want to change still works as it did before. It was first published about 10 years ago, and it's been in an IETF working group for about 8 years, and the initial version was standardized about 3 years ago, and Cisco is shipping something they call Fabric Path, which is basically TRILL, and Brocade has something that they also call something that I've forgotten what. Anyway, but it's TRILL. The basic TRILL concept, TRILL switches find each other because they're either neighbors or they can multicast to each other through a little Ethernet, legacy Ethernet cloud. They calculate paths to other TRILL switches. So they calculate a network that just consists of all the TRILL switches. They ignore all of the Ethernet end nodes. And the first TRILL switch tunnels to the last TRILL switch. So in this case, A transmits a packet to, that's an Ethernet packet. R1 is a TRILL switch. It somehow, and we'll get to that, knows that R2 is the proper last TRILL switch. It puts on a header that says, I'm the first guy, R2 is the last guy, puts it into the TRILL cloud, and the TRILL switch is forward based solely on knowing how to get to R2. And they ignore all the end nodes. Once it gets to R2, R2 removes the header and out pops the original Ethernet packet. So what's in the TRILL header? TRILL switches auto-configure a 2-byte nickname. I hate technology. I'm totally befuddled by cameras and cell phones and whatever. So I believe that things should just work. But then I was told at some point that there's some customers that really like to diddle knobs. And so now I believe that the way you should design it is make it so that it just works if you don't touch anything, but you give them knobs to play with. And they can play with these knobs, but any setting of it still works. So anyway, when I say they auto-configure, if you want, you could configure these addresses if you so choose. And even if you misconfigure, so two have the same, they'll notice it and one of them will take a new address, whatever. So, without even the obnoxious GPS recalculating kind of thing. It'll just do it. So the header contains a 2-byte ingress TRILL switch, a 2-byte egress TRILL switch, a hop count, and flags. So a TRILL encapsulated Ethernet packet, you add this extra 6-byte header to the Ethernet. The TRILL header has 2 bytes for egress, ingress, and then 2 bytes for hop count and flags. So the use of the egress field is a little bit weird. For unicast, it's obvious what the egress field is. It's the last switch. For multicast, it's not clear who it would be because there's lots of switches. So originally, in the original design, there was a single shared tree for all multicast traffic, but some people really wanted to spread the load if you had a lot of multicast. So instead, TRILL calculates several trees, and the first guy who injects it chooses which tree. So here, which is sort of the extent of my ability to do PowerPoint, all these things are supposed to be trees that reach everybody. There's a red tree, a yellow tree, and a blue tree, and when R1 injects it, he chooses which tree by specifying in the egress field. And you can also do pruning inside based on VLAN and IP multicast, but if you're too lazy to do pruning, it just goes along the whole tree, and then at the edge, it decides whether it should forward the packet on. So TRILL switches find each other, creating a network of just TRILL switches. So here I've picked a spanning tree based thing and replaced any subset of the switches. So you kind of compress these Ethernet clouds. Okay, so they just look like clouds of end nodes, and anyway. And the reason for the extra header is that the forwarding table in this TRILL switches just need to be the size of the number of TRILL switches, not the number of end nodes. You have a layer 3 like header that has like a hop count, and it's small and easy to look up addresses. It's 16-bit addresses can be a direct lookup, and that enables you a pretty big cloud of 64,000 switches. You could have hundreds of thousands of end nodes. So I'm assuming I have, because I started 5 minutes late.
Yeah, a couple of minutes.
Right, okay. You're looking all threatening there. So yeah, switches inside the cloud don't. Oh, and you could glue 2 clouds together. So that's another concept that people have, said that, oh wow, there's this whole thing that you can do if you want to glue 2 clouds together and move from one to the other. You can do that with TRILL. What would happen is that S1 and S3 have to be configured. Hey, I want to glue these 2 clouds together. Consider S3 to be a neighbor of yours in TRILL, and then they have to tunnel packets to each other through any sort of technology, just IP and IP, or IP, or TRILL inside of IPsec, or whatever you want. Only S1 and S3 need to know that this new TRILL link between S1 and S3 isn't a direct Ethernet link, but it's a whole path across the internet. Only they have to know. So the advantage of CLNP versus the combination of IP and TRILL is that you don't need ARP. The layer, the flat address space is part of layer 3. On the other hand, there's actually some advantages of IP plus TRILL relative to if we'd done CLNP. So inside the cloud in CLNP, you had to forward based on a 6-byte thing. Here, inside the cloud, you only have to forward based on the 2-byte switches. Also, the routers inside the CLNP cloud have to know where all the end nodes are. Inside a TRILL cloud, you only have to know where the switches are. And also, the fancy features like multipathing, multicast, and VLAN, which allows you to share the same infrastructure and and have separate communities. So another orthogonal concept, I think I'm close to done. Another orthogonal concept is, how does R1 know that R2 is the last switch? And it could be done in various ways. It could be done via learning, that the edge switch learns when it decapsulates data. Or you could configure the edge switches to know where all the MAC addresses are. Or you could have a directory that when the ingress switch doesn't know where it is, it could flood, or it could go ask a directory, hey, you tell me where this is. And it could also do that with the IP packet. Rather than letting an ARP go through, it could, when it has the IP address, it can go to the directory and say, like the DHCP server, and say, hey, you gave out the MAC address, tell me where the MAC address is, and furthermore, tell me which switch it's at. Or you could have a central fabric manager that pushes this table of MAC addresses and which TRILL switch it is to all of the edge guys. Okay, another thing is who encapsulates and decapsulates. Again, this is completely orthogonal. It could be the first switch, or it could be the hypervisor, or it could be the virtual machine, or it could be the application. Having the end node does it saves work for the switch, and it also makes it less likely you'll have a stale entry, because a switch doesn't know if the end node moved necessarily, and it could be sending it into a black hole, whereas the application knows it's not working, and it could throw away what it thought before and relearn through flooding or asking a directory. Recently, there's been a bunch of similar things invented, you know, NVGRE, VXLAN, but these are very similar concepts. I tried to explain this to someone who was saying, no, no, they're completely different. You know, VXLAN tunnels and TRILL encapsulates, or vice versa. I'll never know which one, what's the difference between tunneling and encapsulation. But I think they're exactly the same. And the question is whether the flat address space is based on Ethernet or IP. And you could do either one, but Ethernet seems superior because it has bigger addresses with a smaller header. And everyone knows how to get globally unique Ethernet addresses, whereas you know, auto-configuring unique IP addresses is not as clear. And then the other question is, what do you do with the outer header? In TRILL, it's this 6-byte thing. In VXLAN and NVGRE, it's IP plus UDP plus, you know, whatever. It's much bigger, and there's sort of no notion of auto-configuring like TRILL gets the auto-configured 16-bit addresses. So anyway, so that's basically it. So questions? Yes?